Okay, thank you. So I'll continue on the same topic of computing this map, but I'll just switch from discrete to continuous variables, right? And this is actually what I'm showing is most of the work of my former student, Tiago, and I'll talk some work that I did with Gaussian, not so recent. So just to get everyone on the same page, so I'll be concerned with some product network, which is just this probabilistic circuit, which is smooth and decomposable. And one difference is that I will be assuming that you have univariate distributions at the leaves, right? And instead of having indicators, and so that we can generalize to continuous variables, right? And in particular, I would be concerned with the with models where you have Gaussians on the leaves, right? So this is just representing like a Gaussian distribution with mean 11 and variance 8. So a mode of a probabilistic circuit or of any distribution is just a local maximum, right? It's just a point that, in terms of the density that it represents, you can find some neighborhood where that thing is a maximum. Of course, if you're considering the discrete case, then maybe the neighborhood is something that you need to specify, right? So in the continuous case, usually you would take a ball. In the discrete case, you can take Hamming distance or some bounded Hamming distance, some kind of stuff like that, right? So for this network here, if you just plot the density, you get this image, and then the modes would just be the peaks, right? And why do we want to find modes? Well, one of the reasons is that the modes of the distributions, they are a good summary of your distributions, right? They're a way that you can have to look into the distributions. You know, if you want to like, let's say, transform your distribution, which is, you know, this very complex object in some examples that you can just inspect and see what exactly is my distribution encoding, then you can, the modes are good candidates for that, right? And in a way, you are looking at the maximum of some regions, and then you can see if this local maxima, they make sense or not, right? If they are very probable or not. So you can see if perhaps you are in a region that you have a lot of modes, and that's probably not a very smooth distribution, and that might not be actually a good thing, right? Or maybe it is just the way it is because you are representing very complex data and you might need a lot of modes and so, something like that, right? And if I just give you an arbitrary probabilistic circuit, it might be that you have a single mode, right? And that's probably not a very interesting circuit if that happens. But for us here, that's very interesting. Finding modes is the perfect case. Usually you would have some finite number of modes, but it might also happen that you have infinitely many modes, right? That's a bit weird because I already see Antonio like making bad faces. And I'll talk about that. But even with Gaussian leaves, we don't know if the number of modes is bounded, right? Everybody believes so, but it could happen that you have some very, very bizarre thing and you end up with infinitely many modes, right? Okay, but and of course, if you use just arbitrary continuous distributions at the leaves, then you can easily come up with an example where you just have like a region where everything is a mode, right? Like a donut, right? Okay, so one particular mode that we are often interested in is one that has a high probability, right? Or the highest probability mode, which is like the maximum a posteriori inference, which Benjo just told us about, which is just one particular mode where you consider the region to be the entire domain, right? And then we know something about this. So we know that the problem in discrete networks is NP-hard. We know that it's NP-hard to approximate, and the approximation that we can get gets worse and worse the deeper the network gets. And we know that if we have deterministic or Q-deterministic circuits, then we can do it efficiently, right? And this is actually has let's say a lot of applications, right? All these structured predictions and data imputation, multi-label classification, and stuff like that. So let me just give you some idea of why this is difficult, and it's not very difficult to see. So you have many ways to prove. One way, for instance, is reducing from maximum independent set. So the idea here is that you build this network where each one of the product nodes is just encoding a constraint that if you select that node, then you cannot select its neighbors, right? So for instance, in the first product node there on the left, it's representing node 1 here in this graph, and there's just saying that if you select node 1, then you cannot select the other nodes. And I'm doing this just by placing this indicator distribution here, right? Which just gives ones if x1 is 1 and 0 otherwise. And then for the nodes that are not really connected to all the nodes, you will, to make it smooth, you will have to add some uniform distributions, which is a way of saying I don't care what are the values of those or other variables, right? And then you can show that you have a maximum independent set of certain set, or if and only if the most probable configuration is above some threshold, right? And then because maximum independent set does not allow a very efficient approximation, then you can also show that then some product networks, which is very simple structure, cannot have approximations, right? Cannot have anything better than a linear factor approximation in the number of, yes?
How do you set these values with Gaussian leaves?
Right. So how do you set these variables with Gaussian leaves? I haven't published this, and I thought that given that people have been talking about Gaussian mixture models for so long, someone must have proved this already, right? I've been looking a lot, and I haven't found it. So if someone knows if this already was shown. So I think the trivial way would be just, well, you take all those indicators and you replace it by some very narrow Gaussians, right? And that kind of seems to work, right? Except that, like, if you work with too narrow Gaussians, then the problem is that it's a bit difficult to work with the bounds because you know they go above 1 and so on. So actually, it's not that good to make them very narrow. Actually, it's best to just you leave them as for whatever variance, and you just make them very well spread, right? You just have the whole continuous line to place our Gaussians, right? So you just like create one Gaussian to represent the 0 indicator, one Gaussian to represent the 1 indicator, and you just make these things so far apart that for any practical purposes, it's like they are indicators, right? The proof it's a bit boring because then you have a lot of inequalities, right? So yeah, but I think it works, right? Perhaps it's wrong, but I think it works. There is kind of also another thing that we cannot represent the uniform distributions if we are only using Gaussians, right? But then you can use a Gaussian with just a very wide variance, right? And I think also it works, but it makes for a very boring proof because you have this, everything there. But I think you have the same proofs, right? What I'm not so certain is that if you also get the same approximability properties or no approximability properties, because I mean you have all these numbers and actually you have exponential to something, right? So you kind of have real values there. So I'm not 100% sure that the same no inapproximability results hold if you have Gaussians, but might be. Okay. And then we have seen Yujun show some algorithms how you can do it. There is some other people that have made branch and bound. I have made some not so elegant algorithms. You have this idea of also try to transform to the circuit to make it work. But I think what most people do in practice when they actually want to compute the map is this max product algorithm, which was a very simple idea, which is just like you forget about that this is not really a deterministic circuit. You pretend it is, and you just compute it as it is, right? Which is just the same as saying you greedily optimize over each sum node, right? And then it's quite easy to see that this is just a heuristic, right? So for instance, here I have this very simple network, which is a mixture of two Gaussians with the same weights. And if you plot the density, you can see that the mixture of the two is actually just one Gaussian in the middle, right? And this algorithm, you would always select the mode of one of the components, right? So either this or this. And in this case, it's a bit arbitrary, right? Because they have the same. So we will not select the best one. And you can also see that you would probably select something like here, right? Which would be, I mean, at a bounded distance from the top, right? And that's why I also think that the approximation should still hold. Of course, not because of this example, but because I think you will always, I think you can show that if you are making a mistake, but you can probably find a mode that is a bit close to where you are. But you will not actually find the optimal one, right? Right. So this is a limitation of this method, is that you are always just actually finding a component, right? One of the components, whatever that means when you are actually in a very deep circuit, right? Which is not so clear exactly what a component is in that case. And then one thing is that you can see that the algorithm phase in this very, very simple example where I have two components, one variable, you know, just one sum node. I don't even have product nodes, and right. So yeah. Okay. However, we can easily also show that algorithm it does find some approximation, right? And then the idea is that because the algorithm acts greedily, the one thing that you can show is that, like, when you have product nodes, the algorithm is actually optimal because you are just like optimizing independently in this disjoint scopes. So the problem is actually just when you have the sum nodes. And for instance, if you only have one sum node in your network, then essentially you just have this, right? You can just like manipulate stuff and end up with a circuit like this. And then what you can show is that this guy here will be, by definition, the maximum over all of the other, let's say, inputs of this sum node, right? So if you multiply this value by the number of inputs, you get something that is above the optimal, right? Which is just what I'm showing here, right? So the optimal, it needs to be smaller than moving the maximization in size, which is what the max product algorithm is doing, right? And it cannot be worse than just taking this worst case and placing the same value in all of the input nodes, right? So that means that you get this linear approximation, right? A linear factor approximation by max product. It's not like very good, right? But what we can show is that this is the best possible, right? So we can show that there is nothing better than that. So there is no sublinear, there is no approximation algorithm with a sublinear factor approximation for networks of height 2. So for networks that have at most one sum node. And if you allow more than one sum node, well, more than one layer of sum nodes, then you cannot get anything better than an approximation factor that is like exponential in the size of the circuit, right? Which encodes the number of nodes and edges and so on, right? So in a way, max product is the best thing we can get in the worst case, right? Of course, you can do better when you have a fixed instance, but as a worst case is the best you can do, right? Right. So one thing is that the only thing I did there in that proof is I just showed that you can act greedily, and you can easily find an upper bound, and this upper bound is satisfied by max product. I haven't consider that they were discrete or not, right? There was no mention of what exactly are their univariate distributions. So the same bounds actually apply, the same upper bounds apply for whatever distribution you have in on the leaves, right? As long as you can optimize those distributions, as long as you can find the maximum value of those distributions, right? And then for the lower bound is what I'm saying. I think this is true for Gaussian leaves, but I'm not 100% sure, right? And just to finish talking about this, so we started looking into this because I just talked to Thiago, which was my student, and say, well, you know, people have been doing a lot of work on Gaussian mixture models. So looks like a low-hanging fruit is just like go there, see all the algorithms that they are doing for Gaussian mixture models to find modes of Gaussian mixture models, and just, you know, generalize that to some product networks, right? Look at easy, but then it turned out that essentially there is not that much work in finding modes of Gaussian mixture models, which I find a bit surprising given, you know, how much they are used. And most of the algorithms, they are somehow simple stuff, right? Including the things that we did, right? They're more like gradient ascent or EM, stuff like that, right? So there's the usual. The one thing that I think is a bit different and a bit interesting, but we didn't really have time to pursue this, is this type of continuation methods, right? So the idea is that you smooth out your distribution into something that is easy to find a mode or easier, right? And you do a kind of simulated annealing, right? And then you smooth less and less and less until at some point you are in some region and you stick with that mode, right? And the idea is that if you do it this properly, then you can prove that you can find a mode in an area of high probability, which is what they call significant mode. So not necessarily the mode has high density or high probability, but it's around, it's in a neighborhood of high probability, of high density, right? So for instance, like, I don't know, like this guy here is probably in an area of high probability. So if you draw a ball around this guy, it has most of the mass of the density, but it's not a very high density mode, right? So that's the kind of idea. And so this is a general method. And then for Gaussian mixture models, you have this nice property that is if you convolve a Gaussian mixture with a Gaussian, you get a Gaussian mixture model with some weird variances, but you just get a Gaussian mixture model. So this is interesting. And then you can show that under some conditions, this convolution, if you convolve with a Gaussian that has a very high variance, then you can show that it's a unimodal, right? So it's easy to find the mode of the convolved one. And also you can show a mapping between the modes of the convolved density and the original modes. It's not a trivial mapping because you need to solve a partial differential equation, but you can do it somehow numerically, right? So you have this very convoluted method, but it seems to work really well, and it's quite different from everything that we have been doing, right? And one interesting thing, at least for Antonio, is that actually the method works with negative weights for the mixtures. And in this paper, actually, the guy says that they do have some applications for negative weights, which I don't quite understand. They kind of try to model negative correlation, and they need these negative weights of so mixtures of Gaussians with negative weights, right? So it might be something that someone wants to take a look at that, right? And of course, there is the point of, can we convolve a Gaussian with the sum-product network? I have absolutely no idea, right? So what they do is they have this closed form formula. And of course, then it looks like we could do it because you can just think of, you know, like having all the components of your circuit, but then that would be exponential, and it's not clear if you can do it efficiently, right? But you might be.
If we convolve with an isotropic Gaussian, we just need to add the variance, right? So,
yeah. That's essentially what this is doing. Yeah.
So are you talking about convolving with a full covariance Gaussian, or what? Or, I mean,
well, in our case, it's always isotropic, right? Because I'm assuming the leaves are univariate. This is just, yeah. So what I'm asking is like, okay, this is for a Gaussian mixture model. What if you have a deeper circuit, right? Is this still true?
It can always be squashed to a shallow GMO.
Yes. Yes, but that's not efficient, right?
Yeah, but you really just need to add the variances to the leaves, right? So I guess
it's as a product you can do this because it decomposes.
Yeah.
It's a product of univariate Gaussians,
Right.
which you can think of a circuit that has only a product over univariate Gaussians. things.
right?
It's omni-compatible in the sense you can always do the product with any composable circuit.
Right.
So Antonio and I have a paper called Deconnects, where essentially not with Gaussians, but essentially like with circuits, non-probabilistic circuits, and essentially exactly this idea.
Okay. Okay. So let's talk. That will be very cool. Okay. So this idea of the image is just like this is just some Gaussian mixture model, and when you convolve with the Gaussian, you get this distribution, right? Which is very smooth and has a single mode here. And then if you find the mode here, then you can see that you are in this region of high probability, and then you just do some local search to converge to some other better mode. Right. Okay, so another problem that we might want is not exactly to necessarily find the most probable mode or the mode in a high probability region, but just like find some mode from some region, right? So the idea is that if I give you a starting point, I want to just try to find a mode that has some kind of path from this point to that mode, and that satisfies some iterative procedure, right? And usually the idea is that, of course, you want to have a path of non-decreasing probability, right? Well, what we can show with some reinterpretations of facts is that trying to find if there is an improving point to a current one is also NP-hard. So Bodlander showed this for Bayesian networks, and you can kind of massage his construction to prove that also in probabilistic circuits with discrete inputs. We actually proved something. We were trying to prove some other model about robustness, but in the end, that also implies that finding, an improving model is best than that, which is similar to what we were doing for other reasons. And of course, if the PC is deterministic, you can do it, and you can do it if somehow you define your neighborhood small enough, right? So if you're in the discrete case or even in the continuous case, and you find I just want to find one point that is better than this in some small region, right? And this, for instance, has applications in multiple imputations. So when you have some partial configuration and you want to complete them, but you want to complete in several different ways to get some diversity, right? So you can start from any completion of your model and then try to convert to a different mode, right? And just sample completions. And also in modal clustering, which I'm going to show what's that about. Right, so so what people have been doing in Gaussian mixture models is either gradient ascent, which works reasonably well, but you have all those problems of gradient to define the learning rate and this kind of stuff. And what seems to work a bit better is this idea of Gaussian mean shift, which is kind of a reinterpretation of the mean shift algorithm that people use, long ago. But it's a kind of mean shift where you actually have a model instead of just using the data as a model, right? So you kind of have this complicated equation, but it's actually just simple. It's just saying that you start with some point, you evaluate the density of that point, you kind of renormalize it, right? And kind of compute the sort of expectation of that point with respect to this point, and you get a new point, and you do that over and over again until at some point you converge, and you can show that converges to some mode of the distributions, or it converges to a saddle point, right? It's like, and then like independently, people came up with these variance inference methods, and then they actually showed that this is just the same thing, right? Because this is where mostly like a heuristic. It was just saying, oh, we can do mean shift with the distribution, but yeah. And then people actually derived these equations, and they can show that they are just the same, even though it doesn't really look like the same. So the idea of these modal EMs is just like to have an expectation step where you actually just compute this part here, right? The expectation of this variable, and then a maximization where you try to find as an next point the guy that maximizes this part here. And then the interesting thing is that in this part here, you have the log, right, which makes things easier. Then it's not exactly, it's a kind of finding the mode, but because you have the log there, it makes everything easier, right? And then you can show that you have the same equations above if you make some constraints in the type of models. Right. So, so what we did was just like the obvious thing, right? To transform that to generalize that to some product networks with Gaussian leaves. And the idea is to use these induced circuits. So, an induced circuit is just a decomposition of the circuit, such that you can write the distribution as just this mixture model of these decompositions, right? So for instance, if you have that circuit there on the left, then you can decompose in terms of these trees, and you can add the weights, and the weights will be just the product of all the weights that appear in each decomposition. And then, well, the original circuit is just this weighted mixture of all these trees, right? So you get something like that. Which means that you can have this view of probabilistic circuits as just like a Gaussian, well, a mixture model, right? And if your leaves are Gaussians, then it's just a Gaussian mixture models, except that the number of induced trees is exponential in the size of the circuit. It's just like a Gaussian mixture models with exponentially many components, except also that these components, they actually share some of the parameters, right? So it is, but it isn't, right? Right. So if you just plug in that result here in the equations of the model EM, we can see like the only thing I did was to replace the normal by this product of normals, which comes from one circuit, and then the same thing goes here. So we get exactly the same equations, right? Instead of having the density here, I have the density of some of the induced circuits, and I have this this factor here, which is kind of similar to what we had before, which is just like what you get from the leaves, right? From the Gaussians at the leaves. Right. So of course this is not really efficient because you are summing over an exponential number of things, but because you have this structure of the decomposability of the circuit, you can just actually do efficiently in the circuit, right? So very quickly, let me just tell you how the algorithm works. So we actually have to, because we have actually to compute the numerator part here, and then we have to compute this denominator, right? So we actually propagate like two arrays. So each node needs to compute the numerator and the denominator, and you need to do that for each component of the point that you are computing, right? So this is like the next point, and this is the jth component. And for the jth component, you multiply by the corresponding mean. And for another component, you multiply by a different number, right? So we actually kind of do this all simultaneously, in parallel, right? I think you might have been able to do that with less space and doing 2 passes instead of 1, but we haven't actually tried. All right. So what the algorithm does is that it propagates these 2 arrays. So each array has a value for every variable, right? And then we just propagate from bottom up. We compute these equations. I don't think they're that important, but just to show they're very similar to the standard computations, except you initialize with these weighted Gaussians in the leaves, and everything else is just the same. And then you just return the ratio when you reach the root, right? Okay, and then what we can show is that if I give you a point and I run this algorithm, I get a point that is non-decreasing, right? So it might improve, but it might also converge to a saddle point, right? Which is just something we cannot escape because it's just the property of EM, right? In practice, we see that it's very difficult to converge to a saddle point. Saddle points are very unstable, right? So usually this is not really a big problem. And if you converge to a saddle point, it's usually quite easy to check that it is a saddle point because you can just like perturb the model and you will probably escape the saddle point. Okay. And then why we are doing this? So one thing that we did was like to use that to have more insight into the distribution, right? So this is just like an illustrative example where we use learn SPN to learn a circuit for the 0 digits in the MNIST, and then we try to find all the modes that converges from the data points in the training data, right? And these are actually the small images here, right? And that kind of gives you a view of your distribution, right? So you know that there is a region that is capturing all these different types of handwriting. Right? And then what we did was just we iterated. We started with the modes, learned a new network, right, and converted to the modes again. So then this is the second line here, right? You can think that of the kind of agglomerative clustering, right? It's not so clear if this is actually useful because if you do that too many times, of course, you're just going to end up with the kind of the mean of everything, right? And you have some problems also because these bags there have different sizes, so yeah. But it gives you some insight into the distribution. I think you can use it to try to detect some errors, right? Okay, so just to show another illustrative example, so we just run this model clustering, and then we are just trying to compare the difference between doing clustering using the modes and doing clustering EM style, the typical way that people do, right? So all these modes, they have actually two components, but you can see that the ones on the first column, which are doing model clustering, you actually have more components, right? So the idea is that the modes, they are not limited by the number of components, and all the other methods, they are somehow limited by the number of components. Well, not mean shift, because it's a purely database approach, but also seems to be somehow convergent to the number of components here. Yeah. Whether this is good or bad, then is well, I don't know. So to have something that we can actually have some more understanding if this is good or bad, and we did the same for image segmentation. So it's like a typical task in computer vision. So the idea is that you want to kind of segment your image according to the color and locations of the pixels. So every pixel becomes a data point, and you have like the X and Y location and like the RGB colors. And this gives a data set. We learn a model, and then from the model, we associate each pixel to a color, right? But we don't actually know how many colors we want, right? So what we did was that we built a Gaussian mixture models, right? And just a Gaussian Sum-Product Network with the same structure of a Gaussian mixture model with 6 components, and we are just comparing to k-means here with 6 components just to show that they are different, right? And then one thing that we can do is like we can plot the locations of the modes, and then we are just missing the color of the modes, but the color of the modes are actually what you see in the picture, right? And if you take each point and then map it into the mode that it converges, then you color this image, right? And then you can see, like, the first thing you see that you have many more modes than components. And you can capture some nuance and stuff. So, like, you have the beak of the duck here, which is better represented here than here, right? The idea is that because when you fix the number of components, sometimes you have to make some, like forced to make some decisions. And when you have the modes, you're not forced to make those decisions, right? On the other hand, for instance, you have some artifacts. So you have like a mode here, which is probably just, some nuisance that comes from these two modes, which are closer to the component means. And actually, you just have like very few pixels associated to these modes, right? But I think it's something that you can easily like post-processing and remove those things, right? So I think might be useful. However, you have very specialized and very good algorithms in computer vision for doing this, right? So I'm not really defending this as a, a competitive approach, but it's a kind of generic approach, right? You can do that for whatever, right? You just need a circuit. It's not a very specialized method, right? You can probably find similar applications. Okay, and then just to show you if we increase the number of components, this is actually 30, not 20. What happens, right? So curiously, like when you go from 6 to 10, with 10, you actually just have 10 modes. It might also just be because of the way we learn the networks. But if you go to 20, then you kind of find this very weird frontier here of modes. You know, you have a lot of modes here, right? And then with 30, then also you actually decrease the number of modes, but you also get this weird frontier here of modes, right? So that kind of shows you something about distribution, right? It looks like you are learning a distribution that is, for some reason, too complex over here, right? It shouldn't be that complex. You shouldn't expect to have all these models here, right? So what we wanted to do was like say, can we actually take this and try to improve the distribution? Can we say like somehow learn a simpler model here, right? Well, we didn't have the time to do that, but so that was kind of the idea, right, of this thing. It was more like to refine the model than really use it for this. Okay, and then the last thing is that we can do is to try to find all modes, right? So this is a general strategy that you can think of. Like say, well, first we need to kind of estimate how many modes do we want to find. And then we can try to estimate where we think the modes might be. And then we can just try to run these algorithms that find a mode from some start pointing from each one of these regions, right? So we have at least two things here. One is like to determine the number of modes, and the other is to determine where there might be. And of course, this is kind of related, right? If you know the second, you kind of know the first one, right? The difference is that once you have the regions, you can actually just count how many modes you have found, because sometimes when you run these algorithms, you might actually end up in the same mode, right? And if you knew that you expected to find more modes, but you are just converging to the same ones, then maybe you can like constrain your search so that you don't end up in those modes, right? Okay. So the question is, can we actually even know how many modes a Gaussian mixture model has or a Gaussian sum-product network has? And this is kind of an open question, right? So just to give you an insight, so this is like one of the very illustrative examples where you just have two components, two Gaussians. So it's a kind of small, but these arrows here, they are the components. And you can see that the modes, first, the modes, they are not on the components. But you have some modes that are very close to the components, which is usually the case. And then you have one mode that is very far from any component, right? Which is like in this interaction of the components. And actually, this is the map mode, right? If you want the most probable mode, it's the one that is farthest away from all the possible components, right? So this greedy approach, they probably would fail to find these models, right? You have somehow to know that you want to start around this region to be able to converge this guy, right? Which for this model is kind of simple. You can just consider the orthogonal lines. But one thing you can show is that you can scale this same model to an arbitrary number of distributions. So you take any two components, any two dimensions, number of dimensions, right? You take any two dimensions and you build something like that, right? So you have the degrees of freedom. And then you can show that the number of modes that are far from the components, it grows exponentially in the dimension, right? So you cannot really just try them all, right? Okay, and this is another example, which is I also find kind of illustrative, where again you have the components here, and in this case they are isotropic. They all have the same variance in every coordinate, so every Gaussian has the same variance, and these are the modes, right? And for this case, every mode is a maximum one, right? But you can probably kind of play with stuff and make like this the maximum node or whatever you want, but then you need to not have isotropic Gaussians, right? So yeah, this just shows that the landscape of modes can be quite complicated, right? So what people have been able to show for Gaussian mixture models is if the Gaussians are isotropic, if all the Gaussians have the same variance, then you can show that the modes are inside the convex hull of the components means, right? So this is already something, because then at least we know where to look for the modes. We can start at the components and then kind of refine and look inside and so on. But if you have non-isotropic Gaussians, which I believe like is what we want in practice, then the modes can lie outside the convex hull, which was just the first example. And we don't even know if you draw a hyperrectangle according around the mode components, the modes are there, right? So we really don't know what the modes are here. They could be anywhere, right? So we have no idea actually how to even look for the modes. Of course, we can find some modes, but we don't know if they're the ones we want. What most of the times we do, sometimes we do have data. We learn our models from data, and then the data is actually a good starting point to look for the modes, right? So this is actually we end up doing in practice. And I suspect, I haven't proved, that if you just go deeper in the circuit, you just get more and more complex things, right? So this will just make everything more complicated. Yes?
Modes lie outside the convex hull, or lie outside the min and max bounds for each dimension.
Yeah, so we don't know that. Yeah. So I suspect this is true, but not even that we know if it's really true. Yeah. Right. And then the other thing was, okay, can we at least know how many modes, even if you don't know where they are, because at least we can see, right, if you have found. But yeah, so we also don't know about that. So what people have shown is that, like, if you have any dimensional Gaussian mixture models with only 2 components, you can already have as many as n+1 modes. But if you have more than 2 components, then you can already have exponentially many modes in the dimensions, right? The only upper bound that we have is this thing here. So like to the power of the number of the dimensions of the variables, and then quadratic on the number of nodes, and times this bound here. So this is probably really, really loose, right? So for instance, if you plug in K100 and N50, which is just something that would be not even a very large probabilistic circuit, that's already gives you 10 to the power of 29 possible modes. So yeah, we don't expect to have that many modes, right? Right.
Didn't you say in the beginning that we might have infinitely many ones?
Yes, but that's not for Gaussians, right? Okay, so just to conclude, so this is my defense here, that I think that finding modes is an interesting way to look at your distribution when it's quite complicated. I think it has some useful applications. I think it's a quite challenging problem. I think most people have been looking at the discrete case. It's interesting because in the continuous case, in the Gaussian in particular, there are a lot of things that you can do, right? Doesn't make much sense in the discrete case, and there is also much less work done for the continuous case. Right? So if someone wants to looking for a problem, I think this might be a good idea. There is also a lot of open questions about the modes itself, right? The landscape of mode, how many, where they are. If can you? I'm just talking about location and the numbers, but usually we might be more interested in, say, the modes that are in probable regions, right? In high density regions and stuff like that, right? And I think probably we can show something about that, right? But people haven't shown that. Okay, that's all. Thank you.
Questions? Maybe one.
This mode shifting algorithm, is this actually connected to gradient ascent, and like maybe like that you pre-multiply with some funky positive definite matrix? Is essentially like a So is there a connection?
Yeah, it's variational inference, right? I think you can look at it that way, but you don't derive it from that, right? It's doing gradient ascent in some way, right? But you don't have a learning rate or anything like that, and it's not exactly like a second-ordered method. It's EM, right? It's just EM.
But on the data, right? So.
On the data, yeah.
All right, thanks, Denis, again.
Okay, thank you.
So we'll reconvene at 11:25 for circuits for language models.